everyone. Welcome to episode number 635 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. This week, I am talking all about the advancement of next generation microelectronics with Angelo Dragone and Paul McIntyre from the SLAC National Accelerator Laboratory. Angelo, Paul, and I talk about the mission of the SLAC National Accelerator Laboratory, the details of their new Microelectronics Energy Efficiency Research Center for Advanced Technologies called MEERCAT, the details of a new project with MEERCAT called the Adaptive Ultra-Fast Energy Efficient Intelligent Sensing Technologies, and much more. So, without further ado, please welcome Paul and Angelo to Fish Fry. Hi, Angelo. Thank you so much for joining me.
Thank you, Amelia. It's a pleasure.
Excellent. And hi, Paul. Thank you for joining me.
I'm happy to be here, Amelia. Thank you.
Sure thing. Okay, so we're talking about the advancement of next generation microelectronics today. But first, tell my audience about SLAC National Accelerator Laboratory and your mission.
Well, SLAC is a Office of Science National Laboratory. It's supported primarily by the Department of Energy Office of Science. And as Office of Science suggests, we're a scientific laboratory. We're trying to understand really how the universe works across a wide range of length scales, from subatomic sizes to the size of galaxies and the largest things in the universe, and also across a huge range of time scales, including having capabilities to examine events occurring at the very shortest time scales that relate to the behavior of matter, to chemistry, to biology, and other important topics across all of these different scales. In addition to that, of course, we have to build specialized instrumentation and develop new methods to be able to do these things. And that means we're sort of stewarding the capability not just to do the science, but also to build a lot of the necessary equipment required to do the science.
Angelo, you want to add anything to that?
Yeah, maybe I can expand a little bit about the technologies that we develop here at the lab. We significantly invest in technology R&D to support the science, not only at our own lab, but I would say more broadly across the DOE complex. Our facility and experiments have unique instrumentation needs that push us to develop in-house cutting-edge instruments with specification beyond what is commercially available. So we have an accelerator program, R&D program, that develops new accelerators, which are our sources, radiation sources that we use to probe into new physics. We develop the controls for these facilities, but most of all, we develop the sensing system to collect the data from the experiment. And just to give you an example of something that is nowadays in the news, in the past few years, SLAC led an international collaboration to develop a 3.2 gigapixel CCD-based scientific camera, which is basically the largest digital camera ever built. Now it has been transported to Chile and mounted in the Vera Rubin Observatory. And in the coming years, we'll take detailed images of the southern sky, creating an ultra-wide, ultra-high definition time-lapse recording of the sky. We could say that probably this will be the largest astronomical movie of all time. All these developments rely on advanced microelectronics, and for that, the DOE has a large engineering team working on new microelectronics technology at every level, from research of materials and devices to architecture for sensing and processing data from the experiment. And in many cases, also this development has been applied to other fields. For instance, in medical imaging, there's several developments that came from the research that we do in our report.
That is super cool. Now, as part of a larger endeavor funded by the Department of Energy, SLAC will lead two projects in MEERCAT, or the Microelectronics Energy Efficiency Research Center for Advanced Technologies. So let's talk about MEERCAT. And reducing power consumption and the discovery of new materials are driving forces here, right?
Yeah, that is certainly correct. So with respect to MEERCAT, this is a center composed of 8 research teams from across the country. The teams are based at U.S. Department of Energy laboratories, but also involve extensive collaborations with academia and industry. And really what's driving this is the growing appetite for energy in computing. A lot of that is driven by AI and also blockchain, but just generally the proliferation of computing applications, microelectronic devices throughout the economy is really pushing up demand for electricity. That can be dealt with by expanding supply, of course, but also in the case of MEERCAT, we're looking at ways in which we can use research breakthroughs to reduce the energy consumption of contemporary microelectronics. That involves really a team effort within and across the different projects that have been funded. And it's something well suited to Department of Energy labs because we have unique capabilities at the lab of the sort that Angelo was just discussing. We have that here at SLAC, but also across the Office of Science and DOE labs. So that's an important capability set that we want to leverage in order to deliver new scientific insights and new materials that can enable these lower energy microelectronics.
Maybe I can expand a little bit more on how this center has been structured. So DOE has selected a series of projects through competitive proposal call. The way they selected these projects is in a way that synergies across them could actually be exploited to try to achieve more than what each one of the projects singularly has planned. And so MEERCAT at the center level will actually facilitate the scientific exchange across the projects, coordinate the resources that are available across all the participating institutions to support each one of the projects. In addition, we also intend to create opportunity for further interaction and exchange between MEERCAT and industry. MEERCAT also has an advisory board composed of industry partners that will work basically with the 8 projects and also within the 8 projects, some of them, to make sure the research we conduct can be then in future translated and transferred to industrial application for the benefit of US.
So, Paul, within MEERCAT is a project called ESTEAM, enabling science for transformative energy efficient microelectronics. So, Paul, what's the motivation behind this project and what's the goal for this study?
I think what's motivating us is the fact that when we look at the way that microelectronics is implemented, particularly for computing, the standard kind of architecture involves having logic operations done physically separated from where most of the information is stored in memory. The central processing unit or GPU function will be separate from most of the memory that is in the system. And if we're thinking of an AI type application, where there's continuous process of data being taken in and out of memory for things like matrix multiplication operations, there's a huge amount of energy that's wasted, or a huge fraction of the energy that's wasted in the process of just moving signals through wires from the logic part of the system to the memory part of the system. So in the case of ESTEAM, what we're looking at is ways in which we can break down that bottleneck for data movement. One way to do that is to actually investigate new kinds of devices that include both the memory and logic function in the way that they operate, and in a sense can mimic the behavior of elements of the brain, synapses, for example, in the brain, where much greater energy efficiency can be achieved through sort of the parallel operation of these brain-inspired computing elements. Another approach is to put the memory and the logic together, stack them on top of each other rather than having them be separated far apart from one chip to another. That's another approach that we're looking at, is ways of heterogeneously integrating the logic and memory functions on the same chip to basically make the process more energy efficient. And the third approach is to use light instead of electrons to move data from chip to chip. In some instances can offer real performance advantages and reductions in energy consumption. So a sort of a co-design approach where we're looking at these sort of 3 different strategies, how to trade them off against each other. New materials are required to implement them, and to do this under conditions where real, manufacturing processes could be developed. That's really the mission of ESTEAM, one of the projects within the MEERCAT Center.
Fantastic. Now, Angelo, another part of MEERCAT is a project called the Adaptive Ultra Fast Energy Efficient Intelligent Sensing Technologies. So, can we talk about that as well?
Yes, definitely. We can simply call it Aureis technologies. Aureis in Latin stands for golden technologies. So, as I mentioned before, sensors are critical for collecting data from experiments. And I'd say that along with the broader microelectronics field, we are facing a data deluge problem nowadays. So the increased demand for resolution and speed in our detection system is exploding the amount of data that they produce. And so just to give you an example of the scale, just one typical X-ray camera for SLAC X-ray free electron laser is expected to acquire 1 million frames per second and produce about 40 terabytes of data per second. Now, if you integrate across 1 year of operation, this translates into 1.2 zettabytes of data. This is just 100 times smaller than the entire current data production of the IoT network. So these numbers are huge, and we have to deal with that because they, of course, create a bottleneck in the design of our acquisition system. And also, the data volume that produces is overwhelming the capacity to store data in our facility. So nowadays, we leverage already AI/ML algorithms to process raw data and extract information. And typically, the information that we extract is only a fraction of the total amount of data. So our ACE wants to explore ways to redefine the architecture of sensing network, adding intelligence as close as possible to the data source. This requires adding computing capability distributed across the network and rethinking the AI/ML algorithms that we now use and nowadays are executed in high-performance computing in a way that can actually be operated on resource-limited distributed computing architectures at the edge. As of course, as you can imagine, this requires research to understand how to optimally distribute the computing and communication resources across the network, choose the right type of computing that we could leverage for this application. That could be in the analog domain or in the digital domain. And ideally, it would be great if we could also include the performance parameter of the analog front end, so the very front end part of this microelectronic system that acquires the signals from the sensor, and include those parameters into a data-driven optimization. So imagine, for instance, a camera that could be trained end-to-end and including the front-end parameters like resolution, dynamic range, and sensitivity in a way that they become adaptive with the incoming data. And so these are all aspects of the research that our ACE team will conduct. In addition, also, we will also explore sensor devices that could be deployed in extreme environments. Many of our experiments live in such conditions. And advancing in this area will allow us to develop advanced systems such as diagnostics, for instance, for fusion reactors, which of course is another future path that will allow to boost even more energy production within the country. So maybe I should mention that this last research element that we have in our race is also a point of contact with another DOE microelectronics center, which is called CHIME, stands for Co-Design and Heterogeneous Integration for Microelectronics in Extreme Environment, which of course is, as the name says, focuses on microelectronics for extreme environments. And although SLAC doesn't have a leading role in this center, we are contributing in one of the projects that is led by another national laboratory, Fermilab, that is really focused on sensing in cryogenic environments.
That is super cool. All right, you guys, it is time for your off the cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there. What would you have? Angelo, you go first.
Okay, it's a funny question. Of course, my accent probably reveals my country of origin, which is probably Italy. And so if I would think it's something that I would like from there, it's probably something called bocconotti. It's like a shortbread pastry filled with marzipan and a sour cherry, which I also make very well. So now this forces me to actually act this weekend.
I love it. What about you, Paul?
Well, this is tough. I mean, I'm a foodie, so it's very hard to choose. I will choose something a little bit off the wall, but in the same spirit of Angelo's, I'll go to my ancestral homeland of Scotland and choose haggis. So haggis is somewhat infamous item. It is oats and spices and chopped up innards of a sheep, cooked in a sheep's stomach, boiled, and then it can be sliced up and cooked in a frying pan. You can do all kinds of things with it. So it sounds disgusting. It's actually it's actually very tasty.
And you know what, Paul? I've actually had it. And yes, it is tasty. I will give you that. Well, this was super cool. Thank you so much, Angelo and Paul.
Thank you.
Thank you, Amelia. It's been a pleasure.
Yep.
If you'd like more information about SLAC, I've included a bunch of links below the player on this week's Fish Fryin' page on eejournal.com. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn as well. And we are also on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series and our animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Also, make sure that you subscribe to this here podcast on Spotify, Podbean, Apple Podcasts, YouTube, or just about any other podcasting platform to listen to some exciting upcoming episodes. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of June 6th, 2025, I'm Amelia Dalton, and you've been fried.